Recently, humanoid robots have become increasingly capable of dynamic acrobatic movements. We now regularly see videos online of humanoids running marathons, performing on stage, and even doing parkour. These demonstrations highlight how far motor control and reinforcement learning have advanced. Motivated by this progress, we want to investigate a simpler but still highly dynamic task, whether a Mojoko hopper could learn to execute a front flip.
The initial hypothesis is that behavior cloning, or BC, would converge much faster than pure reinforcement learning approach, while RL might potentially come up with more creative or unconventional flipping mechanism. However, we quickly realized that this task is extremely difficult for pure RL methods because designing a reward for a front flip is surprisingly challenging. This is also known as reward hacking. Since in a front flip, you need to generate enough elevation and tuck for rotation and expand at the right timing to stick the landing. So instead of learning an actual front flip, the hopper often just explode the reward function by repeatedly jumping in the same locations and failing its torso to generate some unstable motions that increase the reward without actually doing the flip. So we also experimented with curriculum learning and other stage pipeline rewards approach, and none of them lead to any success. So later on, we stick to BC and gave up on pure reinforcement learning approaches.
Here's a picture of the hopper, a torso, a thigh, a leg, and a foot. And the challenge was it cannot automatically learn how to do a full front flip and stick the landing by giving them this ultimate goal. The way we solved this problem is like teaching a learner how to dance step by step. We split the whole process down to a handful of key poses. Crouching down first, then launch with the momentum to jump high, tuck to rotate, untuck, land, and stay still. We designed each keyframe well with a successful case, then asked the hopper to learn by behavior cloning. Here's a demo of the flip. It starts by crouching down, loading up energy, then it explodes upward. Once it's in the air, it tucks into a tight ball. The tighter it is, the faster it spins. Then it opens back up to slow itself down, gets ready, and comes in for the landing. The knee bends deep to soak up the impact. The body strengthens and it locks into the place, standing perfectly still.
The major takeaway from this project is that reward hacking is extremely difficult to overcome, especially in highly dynamic acrobatic tasks. Even sophisticated RL techniques like curriculum learning and stage pipeline training often introduce unintended biases and constraints, which led to unstable or unnatural behaviors. Another takeaway is that behavioral cloning can be surprisingly efficient and stable when high-quality demonstrations are available. However, BC also struggles with environment noise and covariance shift, since the policy may fail when it encounters states that were not covered in the expert demonstration. Addressing these limitations would likely require a larger and more diverse expert datasets.